Hello students, welcome back to class. I am Dr. D.S. Veena, Associate Professor in the Department of Basic Science and Humanities, B.V. Raju Institute of Technology, Narsapur. Course name Linear Algebra and Calculus. Topic name Ordinary Differential Equation of First Order and Higher Degree. So students, we are studying about Ordinary Differential Equation of First Order and Higher Degree. If the degree of dy by dx of a differential equation is of first order and of degree higher than 1, then it is convenient to denote dy by dx by p. So if you want to, the form of differential equation of first order and higher degree can be written as f of x comma y comma p is equal to 0. Okay. So where p is nothing but dy by dx. If the degree of dy by dx in a differential equation of first order and of degree higher than 1, then we denote dy by dx is equal to p. The general form of differential equation of first order and of higher degree is f of x comma y comma p is equal to 0, where p is equal to dy by dx. Here we have 3 cases to solve. There are 3 cases. Case 1, equation solved for p. Case 2, equation solved for y. Case 3, equation solved for x. Case 1, equations solvable for p. Case 2, equations solvable for y, and case 3 is equations solvable for x. Now we have here 3 cases to solve. So we will discuss one by one the cases. So first case we will discuss about equations solved for p and solve the problems on them. Case 1. Equations solved for p. Equations solvable for p. Equations solvable for p. Okay. So let p to power of n, p 1 plus p to the power n minus 1, p 2 plus p to the power of n minus 2, p 3 plus so on, plus pn is equal to 0 be an ordinary differential equation of first order and nth degree. So what is it this? Let us take p to power of n p1 plus p1, p to power of n minus 1 p2 plus p to power n minus 2 p3 plus so on plus pn is equal to 0 when ordinary differential equation of first order, because p is nothing but dy by dx. It is of first order and nth degree. Degree is n, where p is equal to, let us take this equation as 1, where p is nothing but dy by dx, and what is capital P1, P2? They are nothing but functions of x and y. Let P1, P2, P3, so on, Pn be some functions of x and y. So if equation 1 is, say, solvable for p, then the LHS of equation 1 can be resolved into factors of degree 1 in p. So let us take, so what I repeat again, if the left hand side of equation 1 is solvable for p, you think, then we can resolve into factors of degree 1 in p. So let us take, say, p minus f1 of x y into p minus f2 x comma y plus on p minus fn xy. So these are how many factors? We are having factor n factors. What is the degree of p? Everywhere it is 1. Okay, so degree 1, it should be resolved in this form. Then we should equate each factor to 0. So if we equate each factors to 0, we get p is equal to f1 xy comma p is equal to f2 xy, so on, p is equal to fn x comma y. Then let the general equation of this be, of equation 1 be f1 x comma y. See, if you solve these equations, we get the general. So f1 x comma y is equal to c, where c is the arbitrary constant. f2 x comma y, c is equal to 0, so on, fn x comma y, c is equal to 0. So you get the solution if you solve these equations. Yes. And what is c? C is nothing but arbitrary constant. We have only one arbitrary constant because the order of the differential equation is 1. To get the general solution, number of arbitrary constants is equal to the order of the differential equation. Since the order is 1, you get one arbitrary constant. So the general solution of 1 is, if you multiply these all solutions, you get f1 xy c is into f2 xy c, so on, fn x comma y, c is equal to 0. So this is the solution. General solution of the given equation 1. So we'll solve the problems now. Let us take one example. Solve x square p square plus 3xy p plus 2y square is equal to 0. So this is the differential equation of first order and degree 2. Okay. So what is p here? P is nothing but dy by dx. So first order degree is 2. So let us solve the problem. Let us take the given equation. What is given? X square p square plus 3xy p plus 2y square is equal to 0. Take this equation as 1. Now we should resolve this into factors such that the degree of p is 1. So let us split this 3xy as x square p square plus, we can write this as xyp plus 2xyp plus 2y square is equal to 0. Why we are doing this way? To take the common terms so that we get factors. So from these two terms, what is common? X, y. So what is common here? X and p. So what do you get? Xp plus y plus what is common in these two terms? 2y 2y is common. So what do you get here? If you take 2y common, so you get xp plus y. So total what is common? xp plus y into xp plus 2y is equal to 0. Now see that we have resolved into factors such the degree of p is 1. We have got two factors. What is the next thing we have to do? We have to equate each factor to 0. So what do you get? xp plus y is equal to 0 and xp plus 2y is equal to 0. We have to solve these equations. So what is now replaced by what is p? So what is p? We have taken dy by dx. So first we'll solve this x dy by dx plus y is equal to 0. So what do you get here? So what do you get here? So we can solve this by variable separable. So x dy by dx is equal to minus y. Separate the variables all x with dx and all y with dy. So we can write this as dy by y is equal to minus dx by x. So how will we solve this? Now here we have separated the variables all y with dy and x with dx. So integrating on both sides. So what do you get? Integrating on both sides, dy by y is equal to minus dx by x. So what is integration of dy by y is nothing but log y is equal to minus log x. So since both are in log, we get integration constant as log c. So we can write it as, applying the laws of log, what we can write? Take this term to RHS, or what we can write this as? Log x is equal to log c. Now apply laws of log. Log y plus log x is nothing but log x into y. So log xy is equal to log c. So remove log on both sides, we get xy is equal to c. So this implies xy minus c is equal to 0. So we got one solution. So we'll solve the next one. What is the next equation? X dy by dx is equal to minus 2y. We are replacing p is equal to dy by dx. We have taken the same thing. So now we solve this by variable separable. So separate all x with dx and all y with dy. So dy by y is equal to minus 2 dx by x. Now integrating on both sides. Integrating on both sides, what do you get? Dy by y is equal to minus 2 dx by x. Okay. So what is integration? Log y is equal to minus 2. What is integration dx by x? Is log x. Now since integration constant both are in log, we can write this as log c. So what do you get here? Log y, take this to LHS, you get plus 2 log x plus log c. So apply the laws of log. Log y plus log x square. So this you can take, this is nothing but equal to, by mistake I have taken, it is 0 log c. So we got log y plus log x square is equal to log c. So applying the laws of log y plus log x square is nothing but log y into x square. So you can write it as log y into x square is equal to log c. Remove both side log, you get x square y is equal to c. So this implies x square y is minus c is equal to 0. So now the general solution of equation 1 is nothing but multiplying these two equations. The general solution of 1 is xy minus c into x square y minus c is equal to 0. So this is the general solution, and we have only one arbitrary constant because the order of the differential equation is 1. Okay, now we'll move to the next case, that is equation solvable for y. Case 2. Equations solvable for y. The given ordinary differential equation is solvable for y means we can write y in terms of x and p. I repeat, the given ordinary differential equation is solvable for y means we can write y in terms of x and p. If the given differential equation is solvable for y, it can be put in the form, y is equal to f of x comma p. Okay, now what you must do next, we should differentiate equation 1 with respect to x. So what do you get? Dy by dx. So dy by dx is nothing but p. So p is equal to dy by dx. You get nothing but function of x, p and dp by dx. F of x, you get a function of x, p and dp by dx. So let us denote it by phi x p dp by dx. Take this equation as 2. So now equation 2 is nothing but differential equation in p and x. Equation 2 is a differential equation in p and x. So we can solve this. The general solution of equation 2 is, you get a general solution containing x, p and arbitrary constant. That is function of x, p and some arbitrary constant c. So take this equation as 3. Okay. Now where c is nothing but the arbitrary constant. Why? Because this is the differential equation in p and x. Solving it, we get the solution as function of x, p and c, where c is the arbitrary constant. Now eliminating p from equation 1 and 3 gives nothing but the general solution. So what is the elimination of p from equation 1 and 3 gives the general solution. Understood here? So if you eliminate p from equation 1 and 3, we get nothing but the general solution. Okay. Now we have some conditions here. Sometimes it is not possible to eliminate p from equation 1 and 3. So that time what you have to do? You have to solve for x and y in terms of p. So you have to solve for x and y in terms of p. That x in terms of p, some function, you get a function x in terms of function of p and c, and y as function of p and c. So these two together contribute the solution as general solution. Okay. So what you have to do, this some conditions you have. Sometimes it is not possible to eliminate p from equation 1 and 3. So that time what you have to do, you should solve for x and y in terms of p, such that x is equal to some function of p and c. You will be having c, some arbitrary constant, and y is some function of p and c. These two together gives nothing but general solution. So we have one more condition here. So other condition is nothing but sometimes you have while solving for we get a equation which does not contain dp by dx. You have the factor, one of the factor you may contain which does not have dp by dx. So if we eliminate p between the factor, that factor in the equation and the equation 1, that solution gives nothing but singular solution. But singular solution you are not having in the syllabus, so you do not consider that. You have only in the syllabus general solution, so you neglect the factor which is not having dp by dx. So once again I repeat, sometimes you will be having the factors which does not contain dp by dx. So you have to, if you eliminate p from between the equation, that factor, and the given equation 1, you get a function of some function of x which does not contain arbitrary constant. That solution is called singular solution. So singular solution you do not have in the syllabus, only you have general solution. So whenever you get a factor which does not contain dp by dx, that time you neglect that term. Okay, so let us take some examples. Example 1, in solver for p, so we are taking solver for y. So solve y is equal to 2px minus x p square. So now here the degree of p is nothing but 2 and order is 1. So it is ordinary differential equation of first order and higher degree. So now here you can see that y is in terms of x and p. So given y is in terms of x and p, so it is solvable for y. Take this equation as 1. So it is solvable for y because y is in terms of x and p, function of x and p. So what is the first condition here? We have to differentiate 1 with respect to x. Differentiating 1 with respect to x. So what do you get? P is equal to dy by dx is equal to, here you have to use product rule, 2p plus uv rule, that is 2p 2x into dp by dx minus, here again you have to use the product rule, p square, difference of x is p square 1, so p square minus x, keep it as it is, difference of p square is 2p dp by dx. So what do you get here? So if you take this p this side, this p will get cancelled, 2p. So p plus 2x dp by dx minus p square minus 2xp dp by dx is equal to 0. Okay. Now this equation you should solve. This is a equation, differential equation in p and x. We have to solve this. Okay. So now how to solve? See here, in these terms, in this term and this term, in this term and in this term, what is common? P. So if you take p common, p you get 1 minus p. So what is common in this term and in this term? So what do you get here? What is common in these two terms? 2x So what is common in these two terms? 2x is common. You get 2x dp by dx. 2x dp by dx is common. So what do you get here? 1 minus p is equal to 0. Throughout what is common? 1 minus p. If you take common, what do you get? P plus 2x dp by dx is equal to 0. Now see here you have two factors. One of the factor, first factor does not contain dp by dx. So what I told that the factor which does not contain dp by dx, using that you get singular solution. So no need of including that term. So you have to neglect this term which does not contain dp by dx. So neglecting the term, the factor which does not contain dp by dx. So what you should consider? Only term, this term. So what do you consider? Consider p plus 2x dp by dx is equal to 0. Okay. So now what you must do now? You should solve this. So you can solve this by variable separable. So p is equal to 2x minus 2x dp by dx. So solve this. dp by dx is equal to minus 2. What do you get here? 2 times you can take it as 2 dp by cross multiply. So you get minus dx by x. 2 dp by cross multiply p, separate the variables, all p with dp and all x with dx. Now we have separated the variables. 1 second. Now solve this by variable separable, all p with dp and all x with dx. So we get 2 dp by p is equal to minus dx by x. So now we have separated, integrating both sides. dp by p is equal to minus dx by x. So now we get 2 integration of dp by dp is nothing but log p is equal to minus log x plus log c we can write because all the terms are in log. So log p square is equal to, you can take this to RHS, LHS, so you get log x is equal to log c. So log a plus b, log b is nothing but log ab. So log x p square is equal to log c. So what is, remove log on both sides, we get x p square is equal to c. So this implies p square is equal to c by x. So we get p square is equal to, what you must do now? We have got this equation as 3. So now we should eliminate. Now let us, how many, 1 is over, we can take this as 2. Now from equation 1 and 2 we should eliminate p. So equation 1 can be written as, equation 1 can be written as y minus xp square is equal to 2px. You can take this as plus y plus xp square is equal to 2px, squaring on both sides. Y plus xp square whole square is equal to 4x square p square. Take this equation 3. Now eliminating p from 2 and 3. So what do you get? Y plus x c by x whole square is equal to 4x square c by x. So what happens? So 1x, this get cancelled. 1x get cancelled here. What do you get here? Answer as y plus c whole square is equal to 4cx. So this is the general solution of 1. So this is the general solution of 1. This is how we solve the equation solver for y. Okay. So now we'll go to case 3, that is the equation solvable for x. Case 3. Case 3. Equations solvable for x. Equations solvable for x. If the given differential equation, if the given differential equation is solved for x, then we can write x in terms of y and p. I repeat once again, if the given differential equation is solvable for x, then we can write in the form of x in terms of y and p, function of y and p. So, if the given ordinary differential equation is solvable for x, it can be put in the form x is equal to f of y comma p. Take this equation as 1. So we can, if the given ordinary differential equation is solved for x, means we can put in the form x in terms of y and p. So what we must do here, there we have differentiated, in solve for y we have differentiated with respect to x. Here solve for x will be differentiated with respect to y. Differentiating 1 with respect to y. So dx by dy is nothing but 1 by p, because dy by dx is p, so dx by dy will be 1 by p. So 1 by p is equal to dx by dy is equal to f y, you get a function of f, that is function of y, p and dp by dy. So if you differentiate 1 with respect to y, we get 1 by p, dx by dy is equal to some function of y, p, dp by dy. Take this equation as 2. Okay. Now this is, the equation 2 is nothing but differential equation in p and y. So we can solve it. Equation 2 is a differential equation in p and y. So we can solve it. So you get a general solution containing y and p. We get, let the general solution of equation 2 be some function of y, p and an arbitrary constant f of y, p, c. Take this equation 3, where c is nothing but arbitrary constant. Now eliminating p between equation 1 and 3, we get the general solution. Okay. The elimination of p from 1 and 3 gives the general solution. Understood here? So if we eliminate p between equation 1 and 3, we get nothing but the general solution. So here also we come across some conditions. Sometimes it is not possible to eliminate p between the equation 1 and 3. That time what you must do, you should solve for x and y in terms of p. Okay, so like x is equal to some function of p and arbitrary constant, y and some function of p and c. So this equation together gives the general solution. So this is called the parametric form. So once again I repeat, sometimes it is not possible to eliminate p between equation 1 and 3. That time what you must do, should solve for x and y such that x and y are in terms of p. So this x and y together you get nothing but the general solution. Okay. So other condition, sometimes the equation 1, that is equation 2, what it is, you get a factor which does not contain dp by dx. If you solve the factor not containing dp by dx and the equation 1, we get nothing but we get a singular solution. So in the syllabus, you're not having singular solution, you are only finding the general solution. So whenever you get a factor which is not contained dp by dy here, there you are having dp by dx. Here if you contain dp by dy, you should neglect that term, that factor which contains dp by dy, same as solvable for y. So once again I repeat, sometimes it is not possible to eliminate p between equation 1 and 3. So now sometimes you get a factor of equation 2 which does not contain dp by dy. So if you solve that equation, that factor and equation 1, we get a singular solution. But that singular solution is not there in the syllabus. Okay, so you are having only general solution. So term which contains dp by dy, the factor which contains dp by dy should be neglected. Okay, once again I repeat, the factor which contains dp by dy should be, which does not contain. The factor which does not contain dp by dy should be neglected. Once I repeat, sometimes equation 2 has a factors which does not contain dp by dy. So if you solve the equation and equation 1, you get a solution which is not having arbitrary constant. That solution is called singular solution. So in the syllabus you are not having singular solution, you have only general solution. So the factor which is not having dp by dy should be neglected. Once again I repeat, the factor which is not having dp by dy should be neglected. So let us solve some problems. In equation solver for x, we are having first example. Solve x p square minus yp minus y is equal to 0. Take this equation as 1. So we can write x in terms of y and p. So let us take an example. Example, solve x p square minus yp minus y is equal to 0. We can write x in terms of y and p such that, so what you can write, x is equal to y into 1 plus p by p square. So take this equation as 1. Now since it is solvable for x, differentiating 1 with respect to y, so what do you get? 1 by p is equal to dx by dy. Now you should differentiate this with respect to y. So UV rule you apply. So we can write this as y into 1 plus p by p square as one term. This is u and this is v. So what you can write here, first differentiating y, you get nothing but 1 plus p by p square into 1 plus y you kept as it, and differentiating this term 1 plus p by p, again using u by v rule, p square into differentiation dp by dx minus 1 plus p, keep it as it is, differentiating p square is nothing but 2p dp by so here dy dp by dy divided by p to power of 4. Okay, so what you get, 1 by p is equal to 1 by p square plus 1 by p. So this term and this term get cancelled. What you get here common? What is common here? Y p, if you take common, y p dp by dy, if you take common, divided by p to power of 4. What do you get common here? P dp by dy we have taken common, p minus p, we get minus 2 minus 2p. So what do you get here? So 0 is equal to 1 by p square, 1 by p square plus 1p get cancelled here, 1p get cancelled here, y by p cube dp by dy minus p minus 2. So if you take this to RHS, so LHS, what do you get? 2 plus p y by p cube dp by dy is equal to 1 by p square. So 1 p get cancelled, p square get cancelled. So what do you get? 2 plus p y by p dp by dy is equal to 1. Now we can solve this by variable separable. So what do you get here? P 2 plus p by p into dp is equal to dy by y. So we have separated the variables, all p with dp and all y with dy. Now integrating on both sides, so what do you get here? 2 by p plus 1 dp is equal to integration dy by y. So what do you get? 2 log p plus p is equal to log y plus log y plus log c. So what do you get here? Applying the laws of log p square minus log y minus log c is equal to p plus p is equal to 0. So log p square by y c plus p is equal to 0. So log p square by pc, so yc is equal to, we can write this p in terms of log, that is nothing but p log e is equal to 0. So what do you get here? Log p square by y 1 by c and between c plus log e to power of p is equal to 0. So what do you get here? So we can write log p square c e to power of p by y, and we can write 0 as log 1. Okay, I'll remove both side log, we get c p square e to power of p by y is equal to 1. Remove log on both sides, so we get y is equal to c p square e to power of p. Okay, so now from take this equation as 2. So it is very difficult to eliminate between 1 and 2. So what you must do now? Equation 1 and 2 both together contributes the general solution, because x is in terms of p and y is in terms of p. Okay, so what is the general solution here? Since it is very difficult to eliminate p between equation 1 and 2, so what you must do? We have to take x and y in terms of p. Already x is in terms of p and y is in terms of p. That gives the general solution. So what is the general solution here? Equation 1 and 2 together constitute the general solution. So what do you get? X is equal to y into 1 plus p by p square, and y is equal to c p square e to power of p. So this gives the general solution of equation 1 in parametric form. So let us solve one more problem. Example. Solve y p square minus 2xp plus y is equal to 0. Take this equation. So we can solve x in terms of, we can write x in terms of y. So how we can write it is 2xp is equal to y p square plus y. So what you can write? 2x is equal to yp plus y by p. So we can write x in terms of y and p. Take this equation as 1. So this is, since we can write x in terms of y and p, so it is solvable for x. When it is solved for x, we can differentiate, we should differentiate equation 1 with respect to y. Differentiating 1 with respect to y. So what do you get? 2 dx by dy is nothing but 1 by p. 2 by p is equal to uv rule, you can apply y and p, you can apply uv rule, p plus y into dp by dy plus 1 by differentiating y, uv rule again, y and 1 by p. Difference of y is nothing but 1 by p minus y by p square dp by dy. Okay. So now here, if you get cancelled here, one term get cancelled. So what do you get here? P plus y dp by dy minus 1 by p minus y by p square dp by dy is equal to 0. Okay. So here in this term, what is common here in these terms? So what is common if you take in this term p as common? So what do you get? P if you take common, 1 minus 1 by p square. Okay. So in these terms what you will take common? Y dp by dy. If you take common, y dp by dy, if you take common, 1 minus 1 by p square. So what is common throughout? 1 minus 1 by p square is common. So what do you get? P plus y dp by dy is equal to 0. So now see, you have resolved two factors. The first factor does not contain dp by dy. So neglecting that term, neglecting the factor which does not contain dp by dy. What do you get? So p plus y dp by dy is equal to 0. So now we have to solve this. This is differential equation in y and p. So solving, we get the general solution. So we can solve this by variable separable. P is equal to minus y dp by dy. So if you separate this by variables, all y with the dy and all p with the dp, we get dp by p is equal to minus dy by y. Integrating on both sides, dp by p is equal to minus dy by y. So log dp by p integration is nothing but log p is equal to minus log c, so log y, plus integration constant is log c. So apply laws of log p is equal to, take this term to LHS. So you get plus log y is equal to log c. So apply laws of log a plus log b is the log ab. So log p plus log y is the log py. Py is equal to log c. Remove both side log, we get py is equal to c. So this implies p is equal to c by y. So from this equation and equation 1, eliminate p. So what? Substituting p is equal to c by y in 1. So what do you get? If you substitute c by y in 1, so 2x is equal to y c by y plus y by c by y. So y get cancelled here. This. So what do you get here? 2x is equal to c plus y square by c. So you get 2x is equal to c plus y square by c. If you take LCM, 2cx is equal to c square plus y square. So this implies y square is equal to 2cx minus c square. So this is the general solution of 1. So we have discussed about ordinary differential equation of first order and higher degree. We have solved the 3 cases and solved the problems on that. So this is all for the today's class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.